Hello everyone, Geom4 just dropped a new patch release. And you might be wondering, is it worth the upgrade? Or, more generally, should we always keep Geom4 up to date? If you are a part of team, this decision might be made for you. But for solo users, my advice is yes, absolutely. Geom4 is constantly evolving, becoming more user-friendly and packed with new features. However, new releases can sometimes bring along a few minor bugs. Personally, I've found a sweet spot. I usually wait for the first patch release. For example, with 11.3.0, I held off until 0.3.1 came out. That way, those initial, more obvious bugs tends to be ironed out. In this video, we're going to dive into the latest Geom4 patch release and walk through the compilation process on macOS. Whether you are upgrading or installing fresh, this tutorial will guide you step by step. Let's get started. Navigating the Geom4 download page can be a bit overwhelming with so many options. As a Mac user, I recommend steering clear of the binary releases. Security settings on macOS can make it very difficult to use binaries compiled on another machine. Binaries are generally more suitable for Windows users. For Mac, the ideal choice is a source code in tar.bz2 format. This provides the smallest download size, giving you the possibility to compile Geom4 tailored to your specific macOS environment. Double-click the downloaded BZ2 file and let the system extract files from it. Open the folder extracted from the BZ2 file, and you should be able to see a file called cmakelist.txt, which contains instructions for CMake to compile Geom4. To learn more about the rationale of CMake, please watch this tutorial about C++ compilation. The Geom4 installation guide lists the prerequisites for compiling Geom4 on Mac, which includes a C++ compiler and CMake. It also recommends us use Homebrew Package Manager to install them. Let's head over to the Homebrew website. Copy the command here by clicking this icon. Click the magnifier to bring up the search box. Type term and hit return to bring up a terminal. Now hold the command key and press V to paste the command we just copied into the terminal. Hit return to run it. Note that you need your password to install Homebrew. This process will also install Xcode command line tools, which include a C++ compiler. Press return to continue. This may take a while because Xcode is large. Be patient and wait for it to finish. At the end of the installation, instructions on next steps will be printed out on screen. Follow them faithfully. Try to copy and paste them line by line to avoid accidental typo. In case you don't know, the key combination of copy on the Mac is to hold Command and press C. The first line here is used to create a file called .z profile in your user's home folder. The second line is used to save the Homebrew configuration into this file. The last line is to run the same command in the current terminal to make Homebrew available immediately in the current terminal. Now the brew command is available for us to install CMake. Note that we will use an option called cask in this command to install not only CMake, but also CMake GUI, the graphic user interface for CMake. Once it's done, click the magnifier and search for CMake. If you can see the three-color triangle, hit return. Click open to bring up the CMake GUI. Now try to drag and drop CMake lists.txt into the CMake window. The location of the Geant4 source code will be filled automatically. It is a good practice to save the compiled file called binaries into another folder called build. So let's type /build at the end of the box. Now click Configure button to start the search for prerequisites. If you see a box asking for access to the download folder, click Allow. Also say yes to allow CMake to create the build folder for you. There is no need to change the default setting for the generator. Simply click Done to continue. Wait for a few seconds for the configuring process to finish. The box in the middle will be filled with red things. Don't worry, there is nothing wrong. Red is just CMake's way to display new values. As long as there is no red text in the bottom text box, everything is just fine. The CMake install prefix variable is used to set the installation folder. I was recommended by a Geant4 developer to set it to my user's home folder instead of a system folder. I normally create a folder for a major release and another one for minor release so that multiple Geant4 releases can coexist in my hard disk. Geant4 relies on multiple datasets to perform various simulations. Some of them are essential, others are optional for the running of Geant4. Check the box here to install all datasets to avoid potential problems later. By default, they will be installed together with the compiled Geant4 libraries, but I prefer to keep them in a separate folder called datasets because they are updated less frequently than the libraries. Some of them can be reused for the next Geant4 release. I use the same datasets folder for all my Geant4 releases. Also check OpenGL, Qt, and Raytracer. They're all useful visualization tools for simulation. Qt also provides a nice graphic user interface for Geant4. I used to recommend beginners to avoid Qt because it takes some extra steps to make it work. Since Geant4 11.3, one can use Qt version 6 instead of 5 with Geant4, which makes the process a bit easier on a Mac. So feel free to enable it if you are compiling a Geant4 version equal or newer than 11.3. Click the Configure button again. And no surprise, we encountered an error related to Qt. It simply says that Qt 5.9 cannot be found. Don't panic. Click OK to get rid of the message box. Click the box here to display advanced configuration variables in the list below. Check the box here to instruct Geant4 to use Qt version 6 instead of 5. Now it's time to go back to our terminal to install Qt using brew install Qt. The default Qt version is already 6. You don't have to do anything else. Wait till the installation finishes. Go back to the CMake window, press Configure, and CMake should be able to find Qt 6 related files automatically. If not, relaunch the CMake window and try again. Now we can click the Generate button to generate makefiles. Wait for a few seconds. When the generating is done, we can close the CMake window and check in our file browser if makefile is really generated in the build folder. Open a terminal in the build folder by right-click here. If you have a magic pad, click with 2 fingers. If you don't see any path bar at the bottom of your file browser, click View and select Show Path Bar to enable it. In the newly opened terminal, use the make command to compile Geom4. To learn more about the make command, please watch the video shown at the top right corner. The time command is optional. I use it to record how long it takes to compile Geom4. The -J6 command is also optional. It is used to specify the number of compilation jobs to run simultaneously. The larger the number is, the faster your compilation becomes. However, it should not be larger than the number of cores of your CPU, or you may crash your system. To find out how many CPU cores you have in your Mac, click the Apple icon, select About this Mac, and click More Info. And then System Report. I have 10 cores, so I eventually launched 8 parallel jobs to compile my Geom4. The system is loaded up to 90% and feels stable. Back to the terminal, we can see that the downloading of datasets and the compilation of source code are processed simultaneously. According to the report of the time command, the whole process took less than 6 minutes. This was the fastest Geom4 compilation I've ever experienced. I'm asked frequently which operating system is good for Geom4 simulation. I think they're all good. There is no need to switch your operating system just to run Geom4. But I have to admit that the latest Mac is very fast. After all the libraries are compiled, run make install to copy them to the installation folder specified by cmake install prefix variable. If your cmake install prefix is set to a system folder, for example, user local, you need to add sudo in front of make install to copy them to the system folder. The output of the installation process shows that Geom4 examples are also installed. This is good for beginners. But if you are an experienced user and don't want to install all the Geom4 examples, search for example in your CMake window and uncheck the box for the advanced CMake variable Geom4 install examples to disable this behavior. The installation process is very fast than the compilation because it mostly just copies files from the build folder to the specified installation folder. I'd like to point out that all the operations we've done in a CMake window can also be done in a terminal using this command. The capital B option is used to create the build folder. The ccmake command is used to bring up something inside the terminal that looks like this, which allows an advanced user to tweak CMake settings using keyboard. I personally prefer this terminal UI to the graphic one because the installation of CMake, Qt, and the later make process are all in the terminal. And the ccmake brings the CMake process into the terminal as well. However, if you are feeling uncomfortable with terminal operations, there is no problem. Just stick with GUI options. After installation, you should be able to see 4 subfolders in the installation folder. Bin stands for binaries, include, lib stands for libraries, and share. The official Geom4 examples are in the share folder. There are 3 executables in the bin folder. However, they're not used to run Geom4. For example, one of them is called geom4.sh. It is used to set up two environment variables for your system to find Geant4 related files. One is called Geant4 data dir. It should point to the folder where your datasets are installed. The other is called path. The bin folder in your new Geant4 installation should be included in it. Use the source command to make this setting in geant4.sh take effect immediately in the current terminal. This is called post-installation process. It is mentioned in the Geant4 installation guide. Post-install setup is very important. If you skip this one, your system won't be able to find your installed Geant4 files. In order to make these settings permanent, you need to use this command to save the source command to the .zsh.env file in your user home folder. Otherwise, these settings will be gone when you close the current terminal. Now, you should be able to run the geant4-config-version command to verify the version of your newly installed Geant4. Geant4-config can be also used to check other aspects of your Geant4 installation. It can be used to install missing datasets, for example. If some datasets are missing in your datasets folder, you can use this command to manually install them. Geant4-config also shows which optional features are enabled in your specific Geant4 installation. For example, we can see that Qt is enabled and Open Inventor is not. Now, let's compile the simplest Geant4 example, basic B1, to verify our Geant4 installation. Open the terminal in the B1 folder. Type cmake -B build to generate a makefile in the build folder. And then type make-C build to use the makefile in this build folder to compile the example. Once done, use the cd command to get into the build folder. Use ls to check if there is an executable called example b1. If yes, use /example b1 to run it. / means the current folder. It is needed for the system to find the example b1 file. In the terminal, we can verify again the version of Geant4. And Qt is one of the UI options. A nice GUI window based on Qt will eventually pop up, showing a few simple shapes and the 3D Geant4 logo. You can press the Run button to shoot a particle through the shapes. Congratulations, you have just run your very first Geant4 simulation. Now what? The shapes here are not the ones that you care about. In order to modify them, you need to learn how to define your own shapes using C++, which is a daunting task. I wrote a very small Geant4 example that is basically just one file with about 60 lines of C++ in it. It is not tied to any specific detector setup and allows you to define your own geometry using simple text instead of C++. I call this type of Geant4 applications universal Geant4 application. Please watch this video to learn more about their advantages. Coming back to the smallest Geant4 example, Mingle. Click on Code, select HTTPS, and click the icon here to copy the line. Open the terminal, type git space clone space, and hold Command press V to paste the line into your terminal. Hit return to download Mingle to your hard disk. Use cd to get into the Mingo folder. Use ls to check if there is cmakelist.txt file in it. If yes, type cmake -B build to generate makefile. We don't need cmake GUI or ccmake to fine-tune any cmake variable. There is not much to turn for this simple program. Once the build process is finished, cd into the build folder, type make to compile it, then sudo make install to copy the compiled Mingo file to user local bin folder. Now use cd space ... to go from the build folder back to its parent folder, Mingo. Type Mingo and hit return to run it here. And you will get the familiar Qt-based GUI. There's no detector geometry showing up here because, as I mentioned, Mingo is not tied up to any detector setup. But if you click the folder icon here to open a file called this.mak in the Mingo folder, it contains many Geant4 macro commands to perform a simulation. And you should be able to see an example detector with some particle trajectories showing up on the Qt canvas. The detector geometry is defined in a file called detector.tg in the Mingo folder. You can open it using TextEdit and change dimensions, locations, and the materials of the detector parts as you like. As promised, no C++ is needed. I have a series of videos and shorts demonstrating how to create detector geometries with very simple text. You can also open this.mak. This is a place for you to specify source particles, their energies, locations, and directions. Again, no C++ is needed for your Geant4 simulation. The Qt-based GUI spent 98 milliseconds trying to deal with a font that doesn't exist on my Mac. This is outrageous. I must get this 98 millisecond back. It turns out that the font is hard-coded in Geant4 source code, interfaces, implementation, src, g4ui qt.cc file. Change it to Baskerville, a font that does exist on my Mac, and save the file. Go to the build folder again and type make there. Make is smart enough to just compile the changed library and leave everything else untouched. This makes this process very fast. Type make install to copy the updated library to the specified installation folder. Run Mingo again, and the warning message is gone for good. However, there is another warning message, but it is more like a piece of information telling us that the default physics list is used because we did not use phys_list environment variable to specify it. But we are cool with the default physics list as beginners.